Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the third continuation of the lecture, Mechanical Vibrations. Well, we have not yet looked at the case where we have a forcing function on the right-hand side. So we're going to look at that, and we're going to look at it in two steps. And the first step we're going to look at is undamped forced vibration. So we do not have a gamma u prime term here, but this is what we're going to look at anyway. So we have this, and this f of t really could be anything, but for the sake of argument, we're going to say suppose it is cosine omega t times an f0. Now, when we look at this, our complementary solution, the solution to the homogeneous part, is going to be, the complementary solution as a function of t is going to be c1 cosine omega 0. That is the fundamental frequency. That is the square root of k over m t plus c2. This is the sine of, again, omega 0, square root of k over t, or square root of k over m times t. So that is the complementary solution. And then to annihilate this, what you would have to do is this would be d squared plus omega squared. And so that means that we would be looking at this as the particular solution that we can substitute in to the original equation. So let's do that. And we have two cases. So we're going to here insist that the omega that we just talked about was not the fundamental frequency. So we plug it in, we do these calculations. You should verify these and set this equal to the right-hand side. Now, and there's some simplification involved here, but one should observe that since omega is not the square root of k over n, this part is not going to be 0, and this is the same factor here. So when you do this, that's, well, it's not 0 anyway, so you can divide by it, and that's what we do, and we find that a is this number, and here b has to be 0. So that means our particular solution is going to be just a times the cosine of omega t. And I'm doing a little bit of an algebra here. I'm factoring out an m, and then I'm going to call k over m omega 0 squared. So anyway, we have a form of the particular solution that looks like this. And then what we have is our complementary solution, but we often have written that as r cosine omega 0 t minus delta, where that is a phase angle. And so you see we can write the solution this way, and it would have worked a similar way if we had a sine sine function to start out with as well. So we worked through the case where omega does not equal omega 0. But now let's consider what happens if omega does equal omega 0. Well, the same thing happens with the complementary solution, but with the particular solution, what happens is that this is going to be d squared plus omega squared whole squared, which will give rise to a factor of t in the particular solution. So it's at cosine omega naught t plus bt sine omega naught t. So when we substitute that into the equation and set it equal to the right-hand side, we have a kind of a complicated looking expression here. You should verify that this happens. But one nice thing that happens is, since we're saying omega does equal omega 0, then what will happen is that this is 0, and so is this 0. So it is much simpler. These two terms are 0, so we just have that we're going to equate the coefficients here, and that one's going to be 0. So, well, I guess that's what I'm saying here. So that means that what we have when we set the coefficients equal for the cosine of omega t, we will have this, and that will say that b is f0 over 2m omega 0, and a will be 0. So that means our particular solution is this. It is f0 times 2m omega 0, but then it is t, omega 0 t. So when we then start putting the solution together, we have u of t is equal to this. That's the complementary solution plus the particular solution, and we could change this into the form r cosine omega 0 t minus delta, the phase shift, plus this. And so we have an equation that looks like this. Now this one is just fine because that is a cosine and that is well behaved. But here you have this factor of t, and as t gets bigger, the sine will still give you oscillation, but the oscillations will get bigger and bigger and bigger. This is a concept called pure resonance, and these vibrations get bigger and bigger and bigger, and eventually vibrations like this would destroy the system that you were trying to build, or that you'd already built perhaps. Wow. Okay, so that's about resonance. Now here's an example. We have a 3 kilogram object attached to a spring. It stretches at this much, and there's no damping in the system, and a forcing function is of this form. F of t is 10 cosine omega t is attached to the object, and we're telling you the system will experience resonance. That tells you things about the system. So if the object is initially displaced 20 centimeters, and look, there's a lot of units you have to deal with here, downward from its equilibrium position, and given a velocity of 10 centimeters per second upward, find the displacement at any time t. You know what to do. Let's see how you did, but we'll see that after we go to 23.4.